Problems based on the total internal reflection. First problem is, in total internal reflection, when the angle of incidence is equal to the critical angle for the pair of media in contact, what will be the angle of refraction? That is given angle of incidence equal to the critical angle, and we have already discussed for the two media 1 and 2, where 1 is the denser media and 2 is the rarer media. When ray incident at an angle of I to the normal, then it bends away from the normal, and angle of refraction is R. For angle of incidence equal to the critical angle, the ray grazes to the boundary of the two media, and in this case angle of refraction is 90 degree. Hence answer is the angle of refraction for the angle of incidence equal to the critical angle is 90 degree. Next question is, a ray of light from a denser medium strikes a rarer medium as shown in the figure. In the figure, rarer medium is suppose air having the refractive index 1 and denser medium has the refractive index mu. Using the Snell's law, refractive index of the first medium is mu into sine of the angle of incidence I. It will be equal to the refractive index of second medium and the sine of the refracted angle, that is R dash. So mu equal to sine R dash by sine I. It is given that angle between the reflected ray and refracted ray is 90 degree. It is 90 degree. Therefore, R plus R dash will also equal to 90 degree. Or we can write R dash is equal to 90 minus R. Also, angle of incidence I will equal to angle of reflection R. So using these values, we will have sine R dash is 90 minus R and I is equal to R, so it is sine R. That is equal to cos R divided by sine R, and it is equal to cot R. This is expression number 1. Using the relation between the refractive index and the critical angle, which is 1 by mu equal to sine IC, we can say it is equation number 2. Now we use equation number 1 and 2, that is multiply 1 and 2. We will have mu into 1 by mu on left hand side and cot R into sine IC, it is on the right hand side. This mu and mu get cancelled. Therefore, sine IC into cot R equal to 1, or sine IC will be equal to 1 by cot R. It can be written as tan R. Therefore, critical angle IC will be equal to sine inverse tan R. Hence, option A is the correct option. Next question is, a ray of light traveling in a transparent medium of refractive index mu falls on the surface separating the medium from air at an angle of incidence 45 degree. So it is given in the question that angle of incidence is 45 degree and ray is traveling from denser to rarer medium, where rarer medium is the air. For which of the following value of mu the ray can be undergo total internal reflection? We know for total internal reflection I should be greater than critical angle, and critical angle is related with refractive index as sine IC equal to 1 by mu. Therefore, using the equation number 1 and 2, we can write that I is greater than IC, and from 2 we can calculate IC equal to sine inverse 1 by mu. So this implies that I is greater than sine inverse 1 by mu, and it can be written as sine I is greater than 1 by mu, or we can also write as mu is greater than 1 by sine I, because mu and sine I both are the positive term. This implies that mu is greater than 1 by sine, and angle of incidence given 45 degree. This implies that mu is greater than 1 by root 2, or mu is greater than root 2. Root 2 is equal to 1.414. So in given option, the option C is the valid answer because 1.50 is greater than the 1.414. Hence the option C is the correct answer. Next question is, a small source of light is 4 meters below the surface of water of refractive index 5 by 3. In order to cut off all the light coming out of the water surface, minimum diameter of the disc placed on the surface of water is. In the figure, S is the source of light from which we have shown three rays. One ray is normal incidence on the water surface and it comes out along the normal. For this, angle of incidence is 0. As the angle of incidence increases, the angle of refraction also increases and we also get the light in the air. For a particular angle of incidence called the critical angle, the angle of refraction becomes 90 degree and the ray after refraction bridges the boundary of the two medias. And if we further increase the angle of incidence greater than critical angle, the phenomena of total internal reflection take place. No light comes out of the water. Total light revolts back after the reflection. So for critical angle, we can write sin IC is equal to 1 by mu. This implies that because mu is given 5 by 3, this is equal to 1 by 5 by 3 or equal to 3 by 5. If we make a right angle triangle, an angle is IC, then sin IC equal to 3 by 5 shows perpendicular oblique hypotenuse. So base is 4 and we can write tan IC is equal to 3 by 4. Now in the figure, the corresponding angle of the critical angle is shown in the triangle say SA and B. Therefore in triangle SAB, tan IC which is equal to 3 by 4 can be written as perpendicular by base. Perpendicular is AB and base is AS. AB we have to find and AS is 4. This implies that AB is equal to the 3 meter. In question, it is asked that the minimum distance or diameter of the disc, because radius is 3 meter, so diameter of the disc required to stop the light coming out of the water will be equal to D, that is equal to 2R, or it is 2AB, that means it is equal to 6 meter. Hence option A is the correct answer. Next question is, for a given incident ray as shown in the figure, satisfying the condition of total internal reflection for this ray, the required refractive index of the prism will be. Here, the angle of incidence shown 45 degree. Therefore, using the Snell's law, we can write that refractive index of air into sine of angle of incidence, that is 45 degree. It will be equal to the refractive index of the media, which is mu, into angle of refraction, that is, suppose it is R. This implies that sin R will be equal to 1 by mu into sine 45 degree, and sine 45 is 1 by root 2, so it is equal to root 2 mu. This is the equation number 2. Now the ray incident on the second interface, and here it get totally internal reflected. So angle of incidence on the second interface will be 90 minus R. Therefore, using the condition of total internal reflection, that is equal to sin IC, that is equal to 1 by mu. This implies that the limiting condition of the total internal reflection is for the angle of incidence, here 90 minus R as per question. So we can write it is 90 minus R equal to 1 by mu, or cos R equal to 1 by mu. This is the equation number 2. Now we want mu, so we have to eliminate R. Therefore, squaring and adding equation 1 and 2, we will have sine square r plus cos square r will be equal to 1 by root 2 mu square plus 1 by mu square. That is equal to 1 by 2 mu square plus 1 by mu square. That is equal to, taking the LCM, we will get 1 plus 2, that is equal to 3 by 2 mu square. And by identity, sine square r and cos square r gives 1. This is equal to 3 by 2 mu square, or mu square equal to 3 by 2, or we can say mu equal to plus minus root 3 by 2. Because refractive index is positive, so we discarded the negative value. Therefore, refractive index is root 3 by 2. This is the answer. Next question is, a light ray is incident perpendicular to one of the face of 90-degree prism. Here A is the angle of the prism, which is 90 degree, and is totally internally reflected at the glass air interface. This is the glass air interface where the incident ray get totally internal reflected. If the angle of the reflection is 45 degree, from the law of reflection, angle of incidence equal to angle of reflection. So angle of incidence will also 45 degree. Then refractive index is, for critical angle, we know that sine IC is equal to 1 by mu, where mu is the refractive index. Here the symbol for the refractive index is given n, so we will use 1 by n. This implies that IC equal to sine inverse 1 by n. Because for total internal reflection, angle of incidence will be greater than the critical angle. In that case, I is greater than sine inverse 1 by n, or sine I is greater than 1 by n. This can be rearranged as n is greater than 1 by sine I, because sine I and n both are positive. Hence, it is equal to 1 by sine. Angle of incidence at the interface BC is 45 degree. So it can be also written as 1 by 1 by root 2, that is equal to root 2. So finally we can write that the angle of refractive index of the media should be greater than root 2. This is the answer. So option B is the correct option. Next question is, a green light is incident from the water to the air water interface at the critical angle theta. Select the correct statement. First statement is, entire spectrum of the visible light will come out of the water at angle of 90 degree to the normal. The spectrum of the visible light whose frequency is less than that of the green light will come out of the air medium. The spectrum of the visible light whose frequency is more than that of the green light will come out of the air medium. And fourth is, entire spectrum of the visible light will come out of the water at various angle of the normal. We know that speed of light equal to frequency into lambda. If we consider that frequency of light is lesser, this implies that wavelength will be higher. And this implies that because refractive index depends on wavelength, and it is given by formula A plus B by lambda square. Therefore, if wavelength increases, that means refractive index will decrease or lesser. And critical angle is related with the refractive index as 1 by mu. Therefore, if mu is lesser, it means sine IC is larger, or we can say critical angle is higher. Because wavelength of the red color is larger than the wavelength of the green color, then the wavelength of the violet color. This implies that the critical angle for the red color is higher than the critical angle of the green color, and it is higher than the critical angle of the violet color. So for red color, critical angle is larger than the green color. This implies that angle of incidence will be lesser than the critical angle. So ray get transmitted. While in case of the violet color, here critical angle of the violet color is lesser than the green color, so angle of incidence is less greater than the critical angle for the violet color. So for violet color, total internal reflection take place. Therefore, the ray get transmitted for the color which have angle of incidence is less than the critical angle, that is for red color. And for red color, wavelength is higher. This implies that frequency is lesser. So option B is the correct option. The spectrum of the visible light whose frequency is less than that of the green light will come out of the air medium. There are the phenomena which are based on the total internal reflection. Number one is working of the optical fiber. Second is brilliance of the diamond. And third is mirage on summer day.